Structural Scientific Reasoning, E+AI Collaboration, and Scalable Preventive TSIHealthApps Part 1, number 1604, April 19, 2026, Gerald C. EclaireMD Foundation. Category: Biomedical System Modeling, Artificial Intelligence, Preventive Medicine. Introduction. Over the past few years, I repeatedly used the same thinking method in many different medical research subjects, no matter the topic. I always follow the same steps. 1. Find the few most important variables. Simple: glucose, SBP, pulse pressure, sleep. 2. Study how these variables influence each other. Example: high glucose weakens blood vessels, high SBP adds mechanical stress. 3. Observe how the values change over time, not just one measurement, but the trend and trajectory curves. 4. Simplify the model by removing unnecessary variables but keeping the real cause-effect relationship. The goal is to keep the real mechanism while making the model simple enough for practical use. Although the biomedical topics may appear different, the underlying reasoning process remains stable. This observation provides insight into both the scientific methodology and a practical, collaborative work model between natural intelligence (NI) and artificial intelligence (AI). Structural scientific reasoning. The structural approach has been applied across multiple biomedical problems, including several recent research examples: TSI stroke, TSI cardiorenal, TSI seizure, VMT viscoplastic energy modeling, VPT viscoplastopology modeling. Trajectory versus snapshot reasoning. Pulse pressure interpreted as a mechanical stress wave indicating vessel stiffness. Sleep interpreted as a recovery variable for the neuroscience system. Neuroplasticity interpreted as an energy demand and recovery process. Simplification of TSI-CVD from 10 variables to 3 variables. Simplification of TSI seizure from 3 variables to 2 variables. Although these research topics belong to different biomedical areas, the underlying reasoning structure remains consistent. Each problem is analyzed by identifying the dominant variables, understanding their interaction relationships, observing trajectory behavior over time, and simplifying the model while preserving pathophysiological and math-physical meaning. This consistency suggests that many biomedical problems can be interpreted as nonlinear dynamic system problems involving stress, strain, energy accumulation, topological geometry patterns, and recover capacity. Although these problems differ in medical context, the reason and pathway remains remarkably consistent. The process usually starts from real-life observations, which are often complicated. From these observations, the most important factors are selected based on how the human body actually works, rather than choosing variables just because they fit statistical formulas. Next, the relationships among these biomedical factors are examined to see how they influence each other, instead of acting independently. In arithmetic terms, this means using multiplication instead of addition, because multiplication reflects interaction and amplification among factors. Then, the changes of these factors are observed over time. Looking at long-term trends helps reveal how the system is gradually changing. Instead of relying on a single measurement such as a lab-tested data, taken at one moment. In this way, the overall direction of the biomedical system becomes visible as a continuous process, similar to watching a movie rather than looking at a single photograph. Through this way, redundant variables are gradually removed, leaving only those primary variables that preserve structure, meaning, and explanatory power. This reasoning style consistently prefers few variables, clear mechanism, thematic meaning, physical interpretability than many variables, statistical fitting, black box correlation. The goal is not to create complicated theory, but to build simple models that preserve the real mechanism and can help save lives. Engineering interpretation of mathematical structure. This approach is closely aligned with classical engineering tradition, where simple structure with strong explanatory power is often preferred over complicated formulations that are difficult to interpret or apply. Arithmetic operators are not treated as neutral symbols. They carry physical meaning. 1. Addition represents independent contributions of variables to multiplication, represents interaction among variables. 3. Division represents normalization relative to a reference condition. 4. Power functions represent nonlinear amplification or sensitivity. This interpretation is common in physics and engineering disciplines, although it is less frequently emphasized in traditional medical literature, where statistical association is often prioritized. The reasoning workflow remains consistent: observe gives structure, gives simplify, gives validate using real trajectory. This represents a structural pattern recognition across domains rather than a linguistic pattern recognition alone. Because of this structural perspective, concepts from mathematics, physics, Engineering, artificial intelligence, psychology, and biomedicine can connect naturally into one continuous framework. The boundaries between academic disciplines become easier to cross because many complex systems share similar structural behavior. For example, emotional instability and borderline personality disorder, vascular damage from diabetes leading to stroke, and material fatigue leading to structural rupture may appear very different on the surface. However, from a total system and structural viewpoints, they all involve accumulation of stress, reduced stability, and eventual failure when the system's tolerance limit is exceeded. Although the physical expressions differ, the underlying mechanism of gradual damage accumulation and threshold crossing can often be described using similar mathematical and physical structure. Structural pattern recognition versus language pattern recognition. When examining a stress-strain energy data table, the brain often reconstructs a geometric structure immediately. Curve direction, curvature behavior, dominance of energy areas, energy-duster ratios, and stability regions become visible on human brain even before any diagram is drawn by computer. Commercial AI tool. This capability develops through decades of accumulated experience across mathematics theories, physics laws, engineering mechanics, semiconductor chip design, topological geometry, viscoplastic energy theory, and system architecture. When I gave the same stress-strain data table to several commercial AI tools and asked them to draw the stress-strain curve diagram, the results were not correct. After many attempts, the generated figures still did not reflect the real mechanical relationship or the trajectory structure contained in the data. This simple test shows that current commercial AI systems mainly process language patterns, but still have limitation in physics-based reasoning, geometric structure recognition, and cause-effect interpretation. Today's AI large language models are highly effective tools for language organization, semantic summarization, transformatting. However, they are not primarily designed for physics-based reasoning, causal model, and geometric reconstruction area interpretation. Mechanism-based structural modeling. Human natural intelligence often processes information through the sequence. Data gives structure, gives geometry, gives meaning, and processing typically follows. Text gives probability, gives text. These two processes are fundamentally different. Role of accumulated knowledge. Another key distinction lies in accumulated experiential knowledge. Human intelligence develops intuition through decades of observation, trial and error, feedback, and cross-domain learning. Knowledge becomes compressed into structural insight, allowing rapid interpretation of new patterns. Longitudinal data collected over many years becomes integrated into geometric intuition regarding system behavior. LLM knowledge represents statistical relationships derived from training data. Although extremely large in scale, it does not represent lived experimental experience or continuously evolving conceptual models derived from direct interaction with physical systems. My training background spans mathematics, physics, engineering mechanics, computer science, topology, artificial intelligence, semiconductor chip design, psychology, physiology, and pathology. Because of this cross-disciplinary training, I naturally interpret disease progression over the past 3.5 decades as a nonlinear, dynamic system problem, rather than simply a statistical classification problem. From this perspective, disease does not appear suddenly. Instead, it develops gradually through the interaction of multiple influential factors over a long period of time. Similar to stress accumulation and structural change in engineering systems, AI technologies are advancing rapidly in scientific machine learning, physics-informed neural networks, symbolic mathematics, and geometric deep learning. However, most current conversational AI systems remain optimized primarily for written communication and artic editing rather than first principles scientific discovery. This simple diagram reconstruction experiment demonstrates that present LLM systems cannot reliably reconstruct physics-based diagrams directly from tabular biomedical data without explicit structural guidance. In AI collaborative workflow, despite these limitations, AI remains extremely useful as an assistant for information searching, articles editing, language translation, structural organization, equation formatting, constant checking, rapid iteration. This explains why the NIPlusAI collaborative workflow is productive for my medical research work since 2024. Natural intelligence contributes creativity, results interpretation, shield insight, mechanism identification, very selection, causal reasoning. Artificial intelligence AI contributes linguistic clarity, writing speed, structural organization, forwarding, consistency, attention, capability, correction for my aging eyesight. Grammar improvement for my second language background. This NIPlusAI collaboration significantly accelerates my research writing process while preserving the conceptual depth built from 44 years of postgraduate study across 12 academic disciplines. Human intelligence remains responsible for identifying meaningful structure, while AI helps transform that structure into readable scientific language. Language intelligence is not equivalent to scientific insight. Scientific insight requires internal structural models, causal understanding, constrained awareness, and long-term accumulation of knowledge. Consistency with the law of protection concept. The multiplicative structure reflects interaction effects among physiological variables. Health risk rarely rises from a single factor alone. Risk increases when multiple stressors act together. This interaction concept resembles engineering fatigue behavior. Moderate load times long duration times reduced structural strength gives eventual failure. Similarly, moderate metabolic stress times moderate mechanical stress times reduced recovery capacity gives increased physiological vulnerability. Application to preventive TSIHealthApps. Based on this structural reasoning framework, a series of TSI-based apps is being developed for release on the Apple App Store as free educational tools. Thus far, I have developed 3 TSI warning tools: stroke, cardio and renal, and seizure mortality diseases resulted from chronic metabolic disorders. Obesity, diabetes, hypertension, dyslipidemia affects approximately 500 million people worldwide. Stroke, cardiovascular disease, chronic kidney diseases, dementia, and certain cancers are strongly associated with long-term metabolic disorders. Many patients may benefit from simple early awareness and warning tools that allow frequent observation of their long-term risk trends through an iPhone app. These apps are designed for preventive education purposes only, not as diagnostic tools. Each goal is to provide a simple tool for users to monitor biomarker changes in their pathophysiological condition, such as body weight, glucose, blood pressure, and sleep hours, using a small number of measurable variables, without requiring personal identity or private information. In addition, these apps are free of charge to everyone. These input variables are already commonly measured in routine health monitoring. Through multiplicative interaction models, users can observe whether their long-term trajectory is moving toward a safer direction or toward a higher stress condition. The purpose is awareness rather than diagnosis. Early awareness may support timely lifestyle adjustment and may reduce the probability of severe medical events later. Engineering basis for population scalability. The variable selection follows a strong engineering principle: minimum variables with maximum pathophysiological meaning. BMI represents baseline body mass, and metabolic load. Glucose represents long-term metabolic stress. Systolic blood pressure represents mechanical vascular load. Pulse pressure PP equals SBP. DBP reflects vascular stiffness condition. Sleep hours represents neural recovery capacity. These 5 inputs capture major components of chronic disease progression: metabolic stress, mechanical stress, structural stiffness, recovery capacity. Because the model requires only a few commonly measured inputs, it is potentially usable globally, including regions with limited medical resources. Privacy-preserving design. Apps do not collect image, address, location, device tracking information. Medical record uploads. Only 5 biomarker inputs are used. This privacy-preserving design reduces barriers to adoption and increases user trust. Many individuals hesitate to use health applications due to privacy concerns. Removal of identity-related data requirements may improve patients' acceptance. Practical product considerations. Successful adoption of technology often depends on simplicities of use. A clear benefit: most users are unlikely to enter 10 to 15 variables daily. However, many individuals already know or can easily obtain body weights, glucose values, blood pressure readings, sleep duration. Low input burden increases likelihood of continued usage. This app also uses a 90-day moving average trend curve to allow users to observe the direction of their health changes, rather than relying on a few isolated values. Trend behavior communicates trajectory more clearly than individual measurements. A motion picture reveals direction more effectively than a single snapshot. This is part 1.